On this episode of This Week in Space, we're talking to Noah Petro about the Lunar Reconnaissance Orbiter and Artemis 3. We're over the moon. Stay with us.
Podcasts you love.
From people you trust.
This is TWiT.
This is This Week in Space, episode number 76, recorded on August 25th, 2023. Over the moon. This episode of This Week in Space is brought to you by Discourse, the online home for your community. Discourse makes it easy to have meaningful conversations and collaborate anytime, anywhere. Visit discourse.org/twit to get 1 month free on all self-serve plans. Hello and welcome to another edition of This Week in Space, the Round the Moon edition. I'm Rod Pyle, editor-in-chief of Ad Astra Magazine for the National Space Society. I'm here with the inarguable Tariq Malik, editor-in-chief of space.com. Hello, sir.
Hello, Rod. How are you doing today?
Well, I'm really good now that we've been joined by our special guest, Dr. Noah Petro. Okay, now get this resume. Chief of the Planetary Geology, Geophysics, and Geochemistry Lab at the Goddard Space Flight Center, project scientist for the Lunar Reconnaissance Orbiter, which we're going to be talking about today, and the Artemis 3 project scientist. Thank you for coming on, Noah.
Oh, well, thank you so much for having me on. It's a joy, a pleasure, and an honor.
That is, well, it's an honor for us. That's a pretty weighty resume. I mean, I grew up during the space race, so I remember some of the scientists and geologists involved with Apollo, and you're stepping right into those shoes. Shoemaker, and those guys.
Yeah, I mean, and huge shoes to fill, right? I mean, this is not done lightly, and being fully aware of the history, trying to learn from them and do, I don't want to say as good a job because they did an exceptional job. We're in a different environment, but live up to the high standard that they set for the rest of us here in the 21st century.
Well, I just have one request, if I may.
Sure.
Since you're going to be there when all this happens this time in this new space race we're in, it's really, if you write books about the space race, which I've written a number of, and you're researching through those documents, it's pretty clear that most people involved with Apollo weren't worrying about what people like me would be looking for 50 or 60 years in the future. Mm-hmm. So there's primary documents, that the references that don't match up, and there's stuff that's missing, and there's stuff that's just kind of, I'll type that later, and little notes and so forth. And it's really fun to crawl through that as if you're, living those days. But sometimes trying to triangulate things if you're writing a piece of history is really a challenge. And I don't think it occurred to them that we'd be doing that.
Interestingly enough, we just finished a meeting an hour or so ago with the internal science team, the NASA Artemis science team. And I talked about that a bit, saying, hey, folks, let's make sure that we're at least meeting the needs of documentation so that 50 years from now, and this is an example I use, someone could go through our stuff, our digital files, and try to piece together, right? We're fortunate that we know what they did back in Apollo was monumental. And again, we're learning from them. And just with the ever so slight eye that, boy, someone's going to have to go through these team conversations or try to understand my digital file structure or make sense of these PowerPoint slides, right? So many things are done differently. The archiving is different now. I've talked to NASA History Office. What can we do? And so we're trying to do the best we can for that future historian to reconstruct what it is that we've done as easily as possible. Again, someone's going to have to go through years worth of Teams chats and understand what it is we did. And oh my goodness gracious.
That's right. It's not going to be like going into the library into the deep back archives and opening a dusty box. You're going to have to use whatever implanted computers we have in our brains to sift through digital PDF archives. Right?
What a nightmare. But we know we're making history, and not that I don't want to sound so arrogant that we're making history. It's happening fast, and we're doing as best we can to ensure that story gets recorded and told.
Well, and it's an interesting problem. We look back at stuff from the space race and it's mostly paper, and now it's mostly digital, and it's going to be an interesting problem to archive that in a permanent fashion, isn't it?
Yeah, and archive it and make sure it's readable 50 years down the line. Yeah, I've been involved with some folks who are trying to resurrect that history. Go back to the 30-track Apollo tapes, and there's only one reader in the world that can get that data off of the tapes.
Don't break that machine. Yeah,
exactly. Or, it's because it's held together by glue and wishes and dreams, right? So much of the history that was made then is in this perilous state, paper, microfiche, and but for the grace of digital archiving, will this stuff live on 50 years from now? Just imagine someone finding a zip drive or a 3.5-inch floppy disk.
A jazz drive, yeah.
Exactly. What would it take to read that now? And it's not as easy as maybe we hope it is. So we're trying to do our best. As government employees, we have digital records keeping requirements, and so we'll at least meet that. But also engaging with the history office to do things like oral histories, which are good ways potentially to, and I know this is, I apologize for going off stream, but this is like hot off the topic, right?
Yeah.
Oral histories can be a good way to reconstruct recent things that may not have a great paper trail, decisions that were made in 2013. Maybe that digital archive doesn't exist, but there's people around who can recollect, okay, we made these decisions and how they fed forward to today.
Well, just so it's said, I'm going to volunteer Tariq to transcribe the history of the Artemis program onto titanium with a chisel. So we'll have chiseled sheets of titanium. All right. I got to do some space jokes here because we're going to lose them if we don't. Here's one. There's no escaping it. With apologies in advance from loyal listener Sean Hart.
Hey, Sean.
Hey, Tariq. An astronaut couple recently got married and decided to honeymoon on the asteroid Ryugu, but they had to cut the honeymoon short. Do you know why?
Why?
They discovered their relationship was on the rocks.
Wait. Nothing.
Oh, no commentary from the editorial team. Okay. Oh, wait, I got another. Did you hear about the intergalactic conspiracy theory that claims crop circles are actually alien circuit diagrams?
No, I didn't hear that one.
I guess they're just plowing ahead with their technological advancements.
I love it.
Okay. Wah, wah. All right. As always, we invite you to spend this year best or worst because you can't do any worse than we do. Don't forget to do us a solid. Make sure to like, subscribe, and all that podcast stuff. And now let's run along to headlines. And this week, I'm turning loose Tariq to do round rover, and we're going to start with India on the moon, a big moment.
That's right. Yeah. So we had a big bit of history on the moon, kind of the inspiration of our episode this week, because India's space research organization landed their Chandrayaan-3 lander Vikram on the moon in the South Polar region. And it was a first for India. They're the fourth country now to soft land on the moon and the first probe ever to visit the South Polar region. And not only that, but now this was on Wednesday, August 23rd, as we're recording this, that they managed to land on the moon. But they deployed their little rover Pragyan, and they showed little videos of it coming off the lander now. So it's off and driving in the South Polar region of the moon. And they are, I guess, I'm probably gonna get a lot of eye rolls, but India is over the moon to be able to do this, especially after Chandrayaan-2 failed in a few years ago to do the same thing. So they took what they learned from that mission. They landed on the moon, first to reach the southern polar region. Lot of excitement there, and it's only a 2-week mission, the lunar day. So we look forward to see what they find there.
So when we say South Polar region, if I understand correctly, it's something like 70 or 75 degrees.
Yeah, it's not like right at the South Pole.
Yeah,
it's in the outer regions, like a circle, like the Arctic Circle would be kind of put out there. But it's still a big challenge. It's a new place that we've never seen before. I know Noah might have thoughts when we talk about the South Pole just in general later to tell us why that's a good place to go. But it's a brand new region of the moon, unlocked forever by India's Vikram lander there. So it's really exciting to see.
All right. So that's India to the moon. And now we have Russia almost to the moon.
That's right. And just days before India landed on the moon, Russia announced that their own lunar lander, the Luna 25 spacecraft, which was also targeting a different crater in the southern polar region of the moon, did not make it. I mean, after a fairly smooth trip out to the moon, going into lunar orbit on August. I think it was the 19th. It was Saturday, last Saturday. Russia did announce that they had a final orbit adjustment, and it went just, I think 50% too long, something like that, and it kicked itself out of orbit, crashed into the lunar surface, and it's a big blow for Russia's renewed moon exploration efforts. This was their first mission since 1976. Yeah, about 47 years. And there was several follow-on missions planned for this: an orbiter, another lander, a sample return mission as well. They're planning a joint cooperative crewed exploration of the moon with China. So there's an investigative committee looking into like what went wrong here as well. But a lot of disappointed folks with that mission team, because they were supposed to land in the southern polar region, a few days before India, make another first there. But we'll see if they're able to learn from that and rebuild. They did announce, I think this week, plans for a follow-on mission to do this in the 2025-2026 timeframe, looking into how that evolves over time.
Well, and we could talk about this another time a little more, but it's you got to be worried if you're part of the of Roscosmos, of how China is going to look at this, given that you're planning in a few years to be working on a joint base. So I suppose there's some concern over that. All right, moving on. Take it away.
Yeah, well, I have like a bit of a fast shotgun, all the other space that's going on, because there was a lot this week. I haven't had a good night's sleep in a long time. As of now, we are 1 month away from the OSIRIS-REx asteroid sample return. That's September 24th. Mark your calendars. It's going to be a very exciting day out in Utah. And the scientists that are with that mission and NASA are really excited. They're doing a dress rehearsal next week. Hopefully we'll find out how that goes, where they're going to practice everything. The Department of Justice, the U.S. Department of Justice, has filed a lawsuit against SpaceX and claiming that they are... I guess they're not hiring folks who are asylum acceptors and whatnot. And this is kind of just in. It just happened late yesterday that we got the news of it. So we're looking in to see like what's going on there. But SpaceX is very busy. They're launching a Starlink, another Starlink satellite launch tonight, 9:30 p.m. tonight Eastern time. If folks want to tune into that as we're recording, and then of course they're going to turn around and launch a Crew 7 mission to the International Space Station for NASA. That's 4 astronauts, very international. Japan, Europe, of course, NASA in the US, and Russia, all flying to the space station this weekend. It was supposed to launch early this morning as we're recording this, was delayed because they wanted to do some more checks on the spacecraft itself. Meanwhile, while that launches on Saturday and we're celebrating India's success, by the way, all of these stories for the most part are on space.com, with the exception of the Department of Justice one that was from Ars Technica that we saw earlier. And but right after SpaceX launches that Crew 7 mission, Japan's H-2A rocket will be launching another moon lander. They call it a moon sniper. It's the slim moon lander. And this thing, I just wanted to point out real quick, this is really weird. It like lands on its side like a landing airplane. I just saw an animation of it earlier, and it has like these little crumple landing balls that it like sets down on. It's pretty crazy, but it's going to go and test a bunch of technologies to make these precise moon landings for the future. It has like object detection technology on it, so it can like be landing and detect an object, make some moves around, and adjust its approach so that it dodges boulders and stuff like that, makes a nice, safe landing. Meanwhile, at the same time, on that mission, they're going to launch the XRISM astrophysics satellite. It's a new, powerful tool to study the cosmos there, and man, then we have Crew 7 docking on Sunday, and there's just a lot going on. So I just wanted to kind of give everyone a big rundown that just the moon stuff that happened this week is not the end of it. There's more moon stuff coming, and of course there's all these astronaut launches and astrophysics flights as well.
All right, so now we know what you're going to be doing for the next 3 years. Thank you for that. We will be back with Noah Petro in just a few moments after this break. Stay with us. This episode of This Week in Space is brought to you by Discourse, the online home for your community. For over a decade, Discourse has made it their mission to make the internet a better place for online communities. By harnessing the power of discussion, real-time chat, and AI, Discourse makes it easy to have meaningful conversations and collaborate with your community anytime and anywhere you choose. If you'd like to create a community, visit discourse.org/twit to get 1 month free on all self-serve plans. Discourse is trusted by some of the largest communities in the world and is open source and powers more than 20,000 online communities. So whether you're just starting out or want to take your community to the next level, there's a plan for you. There's a basic plan for private invite-only communities, a standard plan if you want unlimited members and a public presence, and a business plan for active customer support communities. Jonathan Balaba, who's the developer advocacy lead at Twitch, says Discourse is the most amazing thing we've ever used. We've never experienced software so reliable ever. And that's a heck of a recommendation. One of the biggest advantages to creating your own community with Discourse is that you have your own data. You'll always have access to all of your conversation history, and Discourse will never sell your data to advertisers. That's huge. Discourse really gives you everything you need in one place. So make Discourse the online home for your community. Visit discourse.org/twit to get 1 month free on all self-serve plans. That's discourse.org/twit. So Noah, what an exciting few years you've got coming up. And, you know, it's funny, when you're my age, I'm 66 now. You know, I remember, I think back on the Apollo era, and I think at the time, those old guys who were running the geology experiments and all that, they weren't. They were in their 30s and 40s, and you appear to be a very young guy. And that's a little different than what we've seen from NASA in the last 20 years, where people are sort of, reaching upper age limits. So congratulations on these assignments. This is just so exciting. I can't imagine.
Well, first of all, thank you for thinking I'm a young guy. There are mornings where I don't maybe agree, or my body doesn't agree.
Yeah, but your beard's dark. Look.
It's working its way in there a little bit. 3 kids and a dog will do that to you. But you're right. You know, I was very fortunate when I got my PhD in 2007 to be kind of at the front edge of a new era of lunar scientists. For decades, lunar science wasn't as active. I mean, look, all the things that just happened in this week, it would have taken years, decades to have that number of launches to the moon and missions to the moon. And so when I graduated and entered the workforce, there was a handful of lunar scientists of kind of my age. And now we have an entire workforce that might be sub 45, which is my almost my age now. And so there is this new era of lunar science and of leadership of lunar science. You know, when we meet to have discussions of lunar scientists, there's a handful of the Apollo era that's still around. There's a handful of people who came kind of in the immediate to near aftermath of Apollo. And then there's us young folk, I guess if you want to think 45 is young, who are kind of leading the charge for this next era.
45 is young.
Thank you.
Just depends on your perspective.
Does that mean 46 is also young, Rod? So,
no, not for you.
Okay. Well, can you kind of give us an idea, Noah, of your path to the moon per se? I mean, you mentioned getting your PhD, but you could have pursued any subject, any science or whatnot. I'm curious, were you bit by the moon bug early, the space bug early? What's that path like that got you there?
So it's a path I couldn't have seen coming when I was a kid, but there were really 3 events in my life that led me to get to this point. One was my dad. My father is a huge space aficionado, space history aficionado. And as a kid, we would go to the Air and Space Museum in DC, space museums across the country. And he instilled in me this interest in Apollo. And only after a couple of these museum visits, we were at the Cradle of Aviation Museum in Long Island, and we're looking at the portable life support system, the PLIS, the backpack that the Apollo astronauts wore. And he looks at me and he says, "Okay, do you see this particular component? I built that." And I think, what? And I didn't know, because his first job out of college was working for Hamilton Standard in Windsor Locks, Connecticut, building parts for the portable life support system. I have in my shelf back here a little Hamilton Standard notebook information guide about the Apollo portable life support systems.
Wow.
And so he worked on that for about 2-3 years after college, and left to go to medical school after they built all the parts and were done. This was before even Apollo flew, he was done. So he was in very early on, and had a part in it. And so his interest in Apollo was passed on to me because it was something that he was actively engaged with. And so I had this fascination with Apollo, fascination with the stuff that was done and all things related to the exploration of the moon. I go to high school, 9th grade in New York State, and I take earth science, and the geology bug bit me. And I thought, oh my goodness, geology is a fascinating science. It speaks to me. And I knew very early on as a 9th grader that, boy, geology is awesome and it's something I want to do. Fast forward to college, my first semester, freshman year of college, Bates College in Lewiston, Maine. It was October of 1997. Guest lecturer for a week, Gene Clough at Bates College, comes to talk to the class for 3 days about the geology of the moon. And I had never really appreciated that you could do geology on the moon, or that it was a scientific field in itself. And so that introduction that Gene made of connecting geology and lunar science and presenting it to the class, presenting it to me, that's when I thought, oh, this is something I could see myself doing. Mm-hmm. And it was really that moment where I thought, whoa, this is what I want to do with my career. I had always had the goal of becoming a teacher. So I went through college also getting my certification to teach high school science, because I wanted to do the same thing that my high school science teachers did to me. Fortunately, for my professional career now, I got an opportunity to go to graduate school and study the moon in an era where there were very few people doing that. And here we are.
Wow. Now you are teaching all of us about the moon.
Well, and from
Yep.
aspiring to teaching high school to this is quite a stretch. So you've kind of queued up the perfect segue for the next question. We haven't been back to the moon with humans for a long time, as we all know, 50 years or so. And we haven't done a lot of robotic work up there, mostly orbital. And suddenly it seems like there's a lot happening. So I think if you're a layperson and you just are, sort of reading USA Today tidbits, you may be wondering, gosh, why all this sudden interest in the moon? I keep hearing about this new space race. China and Russia and the US and Japan and India are all trying to get probes there after this long period of quiescence. What queued us up for this moment?
One is looking over the fence at the neighbors. Okay, well, they're sending probes to the moon. We're sending probes to the moon, and it becomes, a bit of a race. But also, it's a very tangible, reachable goal for a space agency. It's, I won't say easier to send a probe to the moon than it is to Mars, but you can get to the moon in 3 days as opposed to several months to Mars. And so for growing space agencies, it becomes a good first destination, right? Let's send a probe to the moon, prove that we can do this, and then maybe go deeper into space. Second is, there's a lot that can be done at the moon with a handful of simple sensors, cameras, radiation detectors, compositional instruments. And lastly, it's just like real estate. Location, location, location. And with the moon, we have, particularly at the lunar poles, we've got potential resources. We have areas that are extremely cold. We have areas that get extended illumination. So there are places on the moon that become immediately, centers of gravity, and not literal centers of gravity, but centers of interest. Hey, we want to understand what's happening here in these areas at the moon, particularly at the South Pole. And I think that's one of the reasons why you find ourselves having multiple missions to the moon going up, rapid fire. And it becomes a really exciting time. I, as a lunar enthusiast, have an incredibly difficult time keeping track of all of the missions that are about to launch, on their way, what's there. And so, never in my wildest dreams did I think that we'd be in this position where I just can't keep it all straight. And yet here we are.
And that's why we asked you to come, because while this is all happening, the Lunar Reconnaissance Orbiter, one of your 2 missions, has been there for 14 years or so, if I've got my math right, since 2009. And the other mission, Artemis 3, is going to be there with people doing more science in just a few years. So you're kind of bookending like this entire period. And you know, you just mentioned like location with resources and whatnot. And I know that Artemis 3 is going to try to find what the story is. Our LRO has kind of seen lots of clues about the hint. Particularly, you mentioned resources, and of course, everyone thinks about water and water ice there. And I guess the big question is, I mean, you know, what have you found, and what do you hope to find at the South Pole that we've never seen before?
Well, you know, there's really two science questions for the South Pole, as I see it, that we want to address. One is the geology. You know, for me, that's kind of the part that I'm most excited about. There's the South Pole of the moon is on the rim of the largest impact crater in the Earth-Moon system. Whoa. It's the oldest crater in the Earth-Moon system that we can recognize. Oh, that's cool. So sort of overprinted on everything in the South Pole is the idea that you have this ancient, gigantic impact crater that sets the stage for the rest of lunar history, because that's the oldest feature. Everything that we see on the moon, all of the Apollo landing sites, all of the places where robotic missions have landed, are on top of the changes to the moon that happened as a result of this gigantic impact crater. So understanding what's going on with that feature, the South Pole-Aitken Basin, is an open question, and you know, provides us with a lot of fodder for questions that we want to answer with Artemis, with other robotic missions. But then you have this unique environment of the South Pole, where you have these deep craters that receive very little or no sunlight. We have the potential hints of volatiles, of water, of ice, of other volatiles that are you know, maybe have carbon or other organic molecules in them. And so we are presented with this really different environment. And just the same way we think of environments on the Earth, whether you have a dry desert or an arid, icy desert like Antarctica, or wetlands, or you know, any of the numbers of unique areas on the Earth that make our planet so special, we have these little environments on the moon that make that area special, the poles of the moon special. And so whether it's Chandrayaan 3 landing in what I would call like a quasi-polar area, not quite at the pole, but not quite equatorial, or what we want to do with Artemis by going to the South Pole, we'll start understanding these really unusual environments that receive, in some places, very little or no sunlight, or areas that have extended illumination, get sunlight more than the 14 and a half days that the Apollo sites did. And so it's really about understanding these unique environments that we want to go to. And that's where the data from LRO have helped the most, because we've had no access. We had, you know, effectively no data for the South Pole until LRO got there.
Yeah, I wish I could place you back in 1972, which is quite a stretch. I'd put you in an EVA suit and have you standing next to Harrison Schmitt on Apollo 14 Apollo 17, when they spotted the orange glass, and you could tap him on the shoulder and say, if you think that's cool, there's water ice down that way. That's really going to blow your mind.
Well, and actually, you know, so I've been this is a hashtag humble brag, right? I've been very fortunate to get to work with Jack a little bit on looking back at Apollo 17 using the data that we have from LRO, and help, help not guide him. Nobody guides Jack. He guides himself, but walk through working with the new data to reinterpret those sites. And the one thing about that orange glass that helped actually lead to this new era of lunar exploration was an analysis that was published in 2008, looking at those orange glass fragments from Apollo 17 and the green glass that was sampled at Apollo 15, and that found water inside the glass. So it's not water that came from terrestrial contamination or water that came from solar wind or anything else like that. It's water that was inside the moon after lunar formation. And that discovery was at the very beginning stages of our realization that the moon was not as dry as we thought it was. There was always the supposition that the moon was bone dry. And actually, they're right, because bone actually has water in it. So yes, the moon is bone dry. There is water inside the moon, on the moon. And so his samples from Apollo 17 and the discovery of orange glass, I think, was part of what put us on the path to this renaissance in lunar exploration, because the idea that there's water on, in, and at the moon is part of why there is this interest in getting back to the lunar surface and getting back to the lunar poles.
So that's a perfect segue to my next question, which is, could you tell us about how, I know that one of the goals of LRO was to try and see if you could spot water on the moon. Mm-hmm. And you had an instrument for that, didn't quite get the results you were hoping for, if I understand correctly. But then that shifted with LCROSS. Can you just talk about that process and that moment a little bit?
Yeah, well, so let's go back. LRO, right? Was the instruments were selected on LRO in 2005 or so, and boy, I mean, I could go to Jim Garvin and thank him for putting this instrument suite together, because the idea was that all of the instruments could individually do a lot, but when you stack the data together and bring it together, you can tell a more robust story. So we actually had multiple instruments on LRO that could help us understand the lunar water story, lunar volatile story. And, we've used all of the instruments together to try to constrain what's going on. And in addition to a U.S. instrument that was on the very first Indian lunar spacecraft, Chandrayaan-1, the Moon Mineralogy Mapper. And so it was, at that time, a combination of instruments that helped get us to where we are today in telling the lunar water story. Now, when we went to the moon, we thought that we would only find water inside those very dark, very cold, permanently shadowed craters at the South Pole. And it turns out that multiple data sets have suggested that water is present at the lunar surface almost everywhere, that it's widespread, that there's a very thin layer, a veneer of water molecules across the lunar surface. And it's in only some places near the poles where we find enhancements or maybe more abundant water or OH. And indeed, that LCROSS experiment, which targeted an area in the South Pole, Cabeus crater, that has the highest, or at least what we think is the highest abundance of water, that kind of gave us our first ground truth measurement of that. They went and touched the moon, blew up a piece of the moon by crashing a spacecraft into it, and we saw what was blown off of the lunar surface and up, and measured what was there. And that set the stage for us understanding, well, we think we know how much water might be present. And unfortunately, it's now been, like you said, 14 years since that experiment, since LCROSS. And now with these missions heading to the South Pole, we'll actually begin to dig in and touch with rovers these volatiles and understand exactly what's there.
That's exciting. All right, we're going to be back with Tariq's next burning question, which I'm sure is a good one, as soon as we take the short break. We'll be right back.
Rod, you flatter me by saying that my questions are good ones, I have to say. Because
everybody post show, everybody says, gosh, Tariq asks good questions. And then there's always this silence about anything I might have said. So I just step back.
Well, I wanted to follow up on something, Noah, that you just said about knowing, or I guess uncovering more of the water story with LRO, with the LCROSS missions, which just as time evolved and you got more and more data, because the 6-year-old in me wants to know, I guess, as of now, how much water, if I could measure it in gallons or whatever, do you think is on the moon? And as a follow-up, what would it taste like if we could drink it? So.
Well, what would it taste like? Well, it won't taste like Tang. It won't, which is unfortunate, I guess. My hope is that it tastes like coffee, because that would be awesome.
Yes.
No. Yes. So first of all, we don't really know until we go there, and the Viper mission will help us understand exactly what form the water, or we actually always misuse water. Water is H2O. Mm-hmm. We don't know how much H2O is at the moon versus how much OH, hydroxyl, is at the moon. And so one of the things that Viper can do is help us make that difference. And one of the, something that LRO did was tell us that, there's hydration, there's OH, there's hydrogen at the moon, but it doesn't help us understand that difference between OH and H2O. Now, the next missions that go, Viper and potentially future orbital missions, can help us differentiate between those two species and hopefully tell us a little bit more about what we can expect there. Now, one of the experiments that'll be on Viper, and we should point out that question.
Just sorry to interrupt. I just want to let our listeners know Viper is a new moon rover that NASA is going to send to the lunar South Pole to help uncover the story. Sorry.
On a private lander. Yeah.
Yeah. Talking about Viper is an amazing thing because this is a mission many years in the making, has gone through different cycles, but a lot of our hopes for understanding what's there ride on that rocket, ride on that rover. And so Viper will help move the story of lunar volatiles along in very important ways, similar to how we expect that samples from Artemis 3 and measurements on the surface from Artemis 3 will do the same thing. You asked what it would taste like. Well, if it goes through the distillation process and the purification process, hopefully it tastes a lot like the water that you get out of, hopefully the clean water you get out of your taps. But of course, there's going to be everything else that's in the lunar regolith, in the lunar surface, that will be mixed in with that. So the process of actually going from buckets of lunar regolith into whatever device it is that's going to extract, boil off that volatile, recollect it, and turn it into something that's usable is going to be complicated. And so the folks who focus on what we call in situ resource utilization are very interested in what the rover, what the Viper rover finds. And, our great hope is that we're able to use those resources that are at the moon, the hydrogen, the oxygen, the water that's there, to sustain a presence with Artemis and use those resources not only on the moon, but in making rocket fuel to go deeper into the solar system.
Well, it's worth mentioning, we often bring this up, we're talking about lunar water. Of course, we're amateurs when it comes to lunar water, but it's expensive to launch water. It's expensive to launch rocket fuel. It's expensive to launch water. And there's a reason when you look at a rocket like the SLS, just that little tiny triangle at the top and a little bit below it is the cargo, and all the rest of it is fuel. So if you can find water off Earth, especially somewhere like the moon, which has 16% of Earth's gravity, what a bargain. The solar systems.
It's location. It's the fourth component of that, right? That it's this small, low gravity environment, literally in our backyard.
So I love talking about water on the moon and what that opens up. But before it gets away from us, can you talk a little bit about LRO's other achievements? Because you've mapped almost the entire moon, which hadn't been done before. You mapped it at a resolution that it wasn't done before. It sounds like from when you were talking earlier about history, it sounds like you might have been involved with, or certainly had an awareness of, the team that was putting back together the Lunar Orbiter materials from years ago at the McDonald's up in Northern California. But LRO it really revolutionized the way we see everything from the lunar surface.
Oh, yeah, no question. I mean, it was, for a mission that was supposed to last 1 year, 2, maybe 3 years, here we are 14 years on. We have, project scientist of LRO, of course, I'm very proud of it. But we have revolutionized our understanding. We have rewritten the textbooks of what we think of the moon. And we've done so, I think, with a level of expertise and just an incredible science team that has pieced together this story. No one has ever studied the moon up close for that long. And so for me, I think one of the results for LRO that I'm most proud of is that we are able to see the surface change. So over 14 years, we snap an image in 2010, 2011, 13, whenever. Comparing those images, we can see how the surface has changed because of micrometeorite bombardment, or because of landslides, or because of, we haven't quite seen a moonquake and the results of a moonquake, but the longer we look, the greater the chances are that we'll see, movement along a fault, along a scarp. We've also seen the results of not only successful landings, but unfortunately also the results of landings that didn't quite go to plan. And so we're actually able to provide the information about what happens when things don't go well, or what happens when things do go well, and what are the effects of landing on the moon and how that changes the surface and the environment around it. And so we're able to provide this now 4-dimensional view of the moon and its environment, not only a static image of what it looks like at one instance in time, but how it's changed. Prior missions to the moon, whether it's the early lunar orbiters, Clementine, Kaguya, they've all effectively provided individual snapshots of the moon. We're able to see the moon change beneath our feet.
And it sounds like there's a direct line, Noah, from the reconnaissance part of the Lunar Reconnaissance Orbiter and your role now as Artemis 3 project scientist there because you want to find the most interesting place to land with astronauts for the first time in the 21st century. You've got this wealth of data now from the last decade and a half from LRO. How has that mission helped shape where you're going to pick from or what you're going to send astronauts to?
I mean, I don't think it's I'm too bold to say that without LRO, we could not do Artemis. I mean, that's why LRO was sent to the moon, was to provide the data to support future robotic and crewed exploration. And so as we're going around identifying where we want to go, the first tool we use is what available LRO data is there. Now we have incredible topography. We have an incredible understanding of the shape of the moon, the nature of the surface. Before I go on, though, we also have an incredible asset in the form of the gravity data that we got from the Grail spacecraft, launched after LRO was there for about a year and provides this incredible insight into the gravity field at the moon. The combination of LRO and Grail data really is a 1-2 punch that I think makes Artemis not only achievable, but achievable without any or very little uncertainty in the moon. I would say that the hardest part about getting to the moon is the engineering, that the mysteries of the moon, while there are many scientific mysteries, the mysteries of the lunar surface and environment are fairly well in hand. And so when you add on top of the gravity data, the topography, we have not just the amazing high resolution images that we get from the LRO camera, we also have temperature data, we have the compositional information, we have the volatile story, we have radar data. And you piece all of those things together, and it's really now a matter of saying, where can we go? And where are we willing to accept risk about what is known, and make it happen? And so one of my jobs in preparing for Artemis is to kind of walk people through the data that we have and how we interpret it, how we can look at an image from LROC, the Lunar Reconnaissance Orbiter camera, or multiple images. Because again, remember for the Apollo, for most of those landing sites, we may have had 1 or 2 images. In the case of Apollo 17, we had high resolution images from Apollo 15. Now, for any one place that we go at the South Pole of the moon in particular, we may have 30, 40 images, the sun at different illumination geometries. And so we can now look at the surface and interrogate the surface in ways that we could only dream of in Apollo, and really use that data to pick the safest landing sites. Of course, safety is going to be primary, but then with those sites, identify, hey, here are the scientific questions that we'll ask while we have crew on the surface.
And I should point out, just because it tickles me, when you talk about the high resolution images coming back from Apollo 15, those came back in a camera magazine because they were on film.
That's right.
Everything was on film. And when you tell people, I do talks for young people, and they, somebody will ask occasionally, hey, how'd they get that picture of the Saturn V second or third stage starting up? You say, well, they had a 16 millimeter movie camera sitting in the adapter shroud. And when that thing separated, it kicked the camera on with a little mechanical switch, and it filmed, and then it parachuted into the ocean. And they're looking at me like, what? I'm sorry, that's a thing with moving parts. What are you talking about? I would like to ask you real quick. Well, I'll ask you after the break. Let's take one more quick break, and then we'll be right back with Rod's burning question. Stay with us. So you had an interesting thing called the, if I get this right, laser communications experiment.
Yeah, that was on the Laddie spacecraft.
Oh, okay. I'm sorry. I thought that was on LRO. Okay.
So, well, actually, so LRO did have a sort of so we've done, okay. Well, so it depends on what definition of laser communications you want to use, because we did a kind of a demonstration using the laser altimeter on LRO to show that you could do communications to a spacecraft at the moon. It was kind of I want to say an ad hoc test. It was obviously very well thought through, but it was not something that we sent to the moon to specifically do. Okay, so here's the full backstory on that, because there was the eventual instrument or experiment that ended up on Laddie. We have on LRO, there was a requirement to know exactly where the spacecraft was in space, down to a few meters maybe, so that we could accurately place our data on the surface of the moon. Having a great high resolution image on the moon of lunar surface is amazing. Not knowing exactly where it falls on the moon, not very useful. And so we had a requirement on the spacecraft to know very accurately where it was in space. And one of the ways that we did that is put on our antenna that we transmit data from the spacecraft down to Earth with a little receiver, a little basically camera that we would shoot a laser at and understand, okay, we shot this laser at this specific time. It took this long to get to the spacecraft. We could use that data to accurately reconstruct where in space LRO was. And one of our brilliant engineers, Xiaoli's son, who has a retroreflector, a small mirror that just landed on the moon on the Chandrayaan-3 mission, recognized that we could use that receiver on the spacecraft that we could shoot a laser pulse to. And instead of shooting a pulse to get timing and position information, we could transmit data that way. And so we actually did an experiment very early on where we just through luck and were able to transmit the Mona Lisa to LRO.
That's what
using
I was
this kind of ad hoc.
We got a link for that. Yeah.
Oh yeah. Invented mechanism. And that was kind of a proof of concept that we could do it. And then we have the laser communications relay device on LADI, and laser comm in deep space now becomes a thing. But it was all through this just kind of, I won't say invented. I mean, it was obviously well thought out, but it was not a requirement on LRO to do this. And therein lies the beauty of having a spacecraft like LRO. We are able to test and use LRO as a test bed for trying things out at the moon and in cislunar space. And so there you have kind of the data as received, using some filters to recreate the beautiful Mona Lisa. And this was done to, again, pave the way for other things. So LRO data paves the way. The ability to test laser communications paves the way. And right now we're testing communications with the Capstone mission, which is at the Earth Moon Lagrange point. Similarly, using LRO as an asset to help NASA and help partner agencies understand what it means to work in lunar orbit.
Well, just a quick follow-up, in watching India and Russia both make their lunar attempts and other countries over the years, NASA, quote unquote, and that's a very big overarching term, but in particular the Planetary and Robotic program, I don't want to say you guys make it look easy, but you kind of make it look easy. I mean, you've got a spacecraft that's designed to do one thing, and then you start saying, well, actually we can do this with that if we want to. That'd be kind of fun. Mm-hmm. And then, coming up on 15 years of operations after this planned year. And of course, everybody thinks of the Mars rover opportunity and so forth, also going 14 years. It's really impressive, but I think we might need a reminder occasionally that it's tough. It may look easy, but it's tough and it's expensive, and it's something, it's expensive for a reason, because if you wanted to send something up there to do one or two things for a short period of time, that's one thing. But if you're building a spacecraft that's intended to be robust, it's existing in this environment with these incredible temperature swings and radiation, bit flipping radiation, all that, it's hard.
Yeah. And that's been as a geologist coming into this, something I had no real appreciation for. And what I've now tried to do is educate my peers and colleagues who don't work on missions. Don't assume that every mission that goes to the moon will last 14 years. LRO has been incredibly lucky. There's not only the space environment, which, as you said, can flip bits and cause chaos on the spacecraft. There's the terrestrial environment. We've managed to sustain funding for this mission now for 14 years, which has taken a lot of work. And we've had times where our budget's been zeroed out, and we've had champions at headquarters that have recognized the importance of having LRO at the moon. We've now written 5 proposals to headquarters for mission extensions that have all been accepted. And so it's not like this has also been given to us. We've worked very hard to make sure that the spacecraft has continued to operate. We've had to invent new modes of operation as parts of the spacecraft have degraded over time. We've invented new ways of controlling and operating the spacecraft that we never imagined, because, well, why would you worry about 14 years of operation? The spacecraft's only going to need to be there for 2 years. And here we are thinking, oh my goodness. And by the way, it wasn't that it was built more robustly than it needed to be. It wasn't that. It was just very well built, very well put together. And fortunately for us, many of those engineers and the people who built LRO, built the parts for LRO, are still at Goddard and still working on the project. And so we can call on them when we have a question. Hey, that thermal blanket that you put on this piece, how would it respond to XYZ? Oh, okay, here's how we have great insight into how the mission works because we have great insight into the people who made it all happen.
You know, thinking back on that time, Noah, and your passion for what is lunar geology, I have to ask if you have like a specific thing that LRO has found. You know, I think that those caves and skylights and stuff are just crazy when I see them, but is there something that really like sticks with you that you will kind of keep with you long after LRO has completed its run, hopefully, decades more in the future. So, but what's your favorite spot on the moon? I guess that LRO has shot.
He's looking exhausted here.
I'm just thinking of all of the proposals that are going to have to be written to make that happen. But if it does, it'd be great, right? Because what better than having a single asset at the moon to do this over time? I would sure love to see the next orbiter get there and be kind of a Landsat style situation where we have multiple orbiters working together. But for now, we have the greatest spacecraft ever constructed orbiting the moon, and let's keep it that way. Favorite things I've seen. I'm going to give you two answers because one is not natural, and these would be the Apollo sites. Being able to see the boot prints, the rover tracks, the hardware that was left behind, the flag shadows for those flags that are still flying at the Apollo sites is one thing that'll always resonate. I'll never forget those first images that came down in the summer of 2009 showing the Apollo sites and thinking, oh my goodness gracious, those are those locations that changed history.
They're footprints.
And we can see them. We can see the hardware that was left behind, and we can see those backpacks that were left behind, those backpacks that my dad built, and we can see them on the surface. And so for me, it's a very personal, but also very meaningful spot to see those images of the Apollo sites. The natural environment, the natural things that we see, and you said it correctly, we had those surprises of finding those lunar pits, those possible caves, seeing tectonic features across the entire lunar surface. I think for me, there's areas on the far side of the moon that I studied for my undergraduate degree that I used the best available data for. This was in 2001. I used Clementine data, and we had one image from Lunar Orbiter of these places, specifically the Oppenheimer crater on the far side of the moon. Not only is there a movie about Oppenheimer, there's a crater on the moon called Oppenheimer, and I studied it for my thesis. And now to be able to look at that spot that I spent a better part of a year studying and see it in exquisite detail with different data sets is to me very, very satisfying, because all of those things where I squinted at images and thought, what is actually there? You can look at it now and say, okay, those dark areas inside the crater, those are definitely pyroclastic deposits, similar to the orange glass that was found at Apollo 17. We now see pyroclastic deposits in beautiful detail across the interior of Oppenheimer crater. We can also see how what their composition is using data from the Diviner instrument on LRO or the Moon Mineralogy Mapper instrument that flew in Chandrayaan-1. We can bring together all of these data sets and tell a comprehensive story of what's going on there because we have multiple data sets from multiple spacecraft that help tell a very exciting and interesting story. So for me, it's about looking at places that I thought I knew and loved, and now looking at them at a detail that I didn't have in 2001 and say, oh, wow, it's even better than I expected.
So looking ahead to the Artemis landings, starting with Artemis 3, I suppose, what if any interaction will there be between LRO and those landings requirements, and also possibly other spacecraft in orbit?
So if LRO is around when Artemis 3 lands, and that's a question, right? There's no guarantee that LRO will be around. We cannot assume that it will. I think I'd like to assume that it's going to be there, but space is a risky environment and anything can happen. But if LRO is at the moon when Artemis 3 is landing, for instance, we're going to want to get images from the spacecraft from LRO showing the lander on the surface so we can know exactly where they are. We'll be able to use instruments on LRO to understand how the environment at the moon has changed. Those landings, as we saw with the Chandrayaan 3 landing the other day, there's a lot of exhaust that comes out of those landers, and particularly with Artemis, we're going to have a giant rocket landing on the surface of the moon. So understanding how the environment, the exosphere, think of it as a very, very weak atmosphere, changes, LRO will help tell that story. And so I think for me, the exciting part will be having this, when Artemis 3 happens, LRO will have gotten its driver's license, might be college aged at that point, all of these milestones for the mission, but also substantially, contributing to our understanding of what happened as a result of Artemis 3's landing. And so it's going to be a wonderful deep space handshake between, Artemis 3 doing its thing, Artemis, 2 will have flown by the moon by that point, and LRO will be silently orbiting the moon, just telling us the story.
I think that kind of leads right into our last question, Noah, which is, I was going to ask, what's like right up in the immediate future for LRO, but it sounds like that's what it is. Be the sentinel to wait for those landers, and then show how that get. But how you mentioned that the spacecraft has forced you, or I guess challenged you, to learn new ways of operating as parts have degraded, and I guess that kind of comes up to the final question of how long do you think LRO has left to go, or is it really like, finding new ways, like it's in the best fighting shape ever, for lasting in lunar orbit?
So, getting roadside repair in lunar space is hard. So as things degrade on the spacecraft, we've been very fortunate that we haven't had any catastrophic failures, that we've been able to see systems degrade and say, well, let's come up with a mode where we don't need to use our reaction wheels on the spacecraft to manage momentum. Pointing the spacecraft down towards the moon, slewing off of nadir and looking off to the side, all require things inside the spacecraft to work. And so we've invented new ways to basically keep the spacecraft operational. All of these have taken time, but we're very fortunate, as I said before, to have the engineers, the people who built the systems down the hall, able to help us address problems and get ahead of them. And so I'd always thought to me that fuel might be the one resource on the spacecraft. Again, can't refuel LRO right now. And we have just gone through a test to basically turn off our fuel use for the better part of 3 months. One of the unknown, there's a lot about operating a spacecraft that just people don't maybe understand or appreciate, but keeping those reaction wheels, which are spinning inside the spacecraft so that we can point in a very accurate direction, requires weekly or at least monthly little burns on the spacecraft just to torque the spacecraft a little bit to shed this momentum inside the reaction wheels. Well, all of that fuel use adds up over time, even if it's just 1/10 of a kilogram here, 1/10 of a kilogram there, it adds up. So we posed the question to the engineering team, well, how do we stop doing that? And we went through effectively 3 months of not doing any fuel maneuvers, using fuel for anything, the longest we'd ever done it. And that shows us a possible path to reducing or eliminating fuel use from our standard operating procedure. And that may have bought us another 3-year extension.
Wow.
We want to keep a certain amount of fuel on the spacecraft in case there's an emergency, in case there's something that has to happen where we need to use fuel. We don't want to be a position where the fuel gauge is on empty. Then the question becomes the battery that we have on the spacecraft. Every cell phone user knows that over time, battery use degrades. Same is true on a spacecraft orbiting the moon. And so we monitor very closely how our battery charges and discharges and charges and discharges. And we'll find out soon. The engineers who monitor our battery will give us a report, sort of an estimate of what they think our useful life is. The good news is that right now, or at least the most recent time we got an update on the battery, we have 100% margin on the battery. So it has, while it has degraded, it's degraded to a point where it's still not going to impact our operations. So I'm comfortable saying right now that we're going to propose for another 3-year extension for LRO, which would take us from the end of 2025 to the end of 2028. and keep us operating. And actually, let me just add one more thing, because it's not just supporting Artemis that we're going to be doing, but also supporting all of these small commercial missions that are going to the moon, what NASA's calling the commercial lunar payload services, where we're paying for rides to the moon to get experiments to the lunar surface. And all of those missions require additional data to assess landing sites. So we are now serving not just the science community, not just the Artemis community, but also the small robotic lander community to get those missions to the moon. And that's keeping us very busy.
Yeah, that Viper mission we talked about earlier, like Rod pointed out, is landing on a commercial lander. So
exactly.
Wow, that is crazy. 2028. That's 20 years. No, yeah. Right? Is that my
almost?
Yeah.
Yeah. I mean, and which is remarkable. At that point, and I've never been great at math, so I'm not going to do it off the top of my head. If we get to that point where we actually are operating as a science mission in 2028, that will, attention must be paid, right? That's going to be something that we all have to take a moment and say, holy smokes, what did it take to get to that point? And it took brilliant engineers and brilliant managers and to get us to that point. Oftentimes those phrases, brilliant managers, don't get used together, but boy, it really did.
Wow.
So I just have to say before I close, to hear you say, well, I'm not great at math. The reason I'm doing what I'm doing now is because I wasn't great at math. I took all this geology in college and then suddenly realized, you have to actually be a capable mathematician to finish this program, especially the PhD. But I appreciate your modesty. Thank you for joining us today. It's been an amazing update. Everybody will keep their eye on moon.nasa.gov, which is great, because I had that the Goddard website in here, and I thought, how am I going to read that so that anybody remember it? So moon.nasa.gov is easy. Is there a place where we can keep up with what you're up to on Twitter or X or somewhere?
So you're definitely, and I, not that I would say people should go follow me on X, because oftentimes, I'll post lunar information, but then I'll post, about the local sports team or other things of interest. But I am on social media at NE-Petro. But don't bother with me. Go to @NASA Moon. And that's where you get the real information. And that's where the real excitement will happen. And to keep abreast of what's going on with LRO, with CLIPS, and of course with Artemis.
Fabulous. And Tariq, where can we keep up with your inarguable exploits?
I should point out, by the way, speaking about the moon, it's a blue moon next week, by the way, August 30th. Set your calendars. But you can find me mooning over that blue moon next week on X, formerly known as Twitter, at Tariq J. Malik, at space.com, as always, where we're looking forward to all of the great discoveries about the moon from NASA and beyond. And if you like video games, you can find me on YouTube at Spacetron Plays. So and this weekend I'll be playing all the new Eclipse stuff in Fortnite, which I'm really excited about.
Okay, yeah, we're thrilled. And of course, you can always find me at pylebooks.com and at adastroMagazine.com. Please don't forget to drop us a line at twit.tv. That's TWIS at twit.tv. We welcome your comments, suggestions, ideas, and I answer each and every single email. But we love getting your feedback. And don't forget to check out space.com. Of course, the website's in the name, and the National Space Society at nss.org. These are both great places to keep abreast of what's going on, along with the previous site we've mentioned, moon.nasa.gov. New episodes of this podcast publish every Friday in your favorite podcatcher, so please subscribe, tell your friends, and give us reviews. We'll take what we can get. And don't forget, you can get all the great programming on the TWiT network ad-free at Club TWiT, as well as some extras that are only available there for just $7 a month. That's cheaper than the coffee I drank during this podcast. Finally, you can follow the TWiT Tech Podcast Network at TWiT on Twitter and on Facebook, and twit.tv on Instagram. Thank you, everyone. It's been a pleasure, and we'll see you next week.
Hey there, Scott Wilkinson here. In case you hadn't heard, Home Theater Geeks is back. Each week, I bring you the latest audio-video news, tips and tricks to get the most out of your AV system, product reviews, and more. You can enjoy Home Theater Geeks only if you're a member of Club TWiT, which costs $7 a month, or you can subscribe to Home Theater Geeks by itself for only $2.99 a month. I hope you'll join me for a weekly dose of home theater geekitude.